This MOOPIL series of Texas A&M University is provided through Project LISTO. Literacy-infused science using technology innovation opportunities. The video series is comprised of experts in the field talking about their research while making important contributions to the art of teaching in the K-12 environment. Project LISTO is funded through a competitive I-3 grant from the U.S. Department of Education Investing in Innovation program. The LISTO project is a collaboration among the Center for Research and Development in Dual Language and Literacy Acquisition, Education Leadership Research Center, and Aggie STEM.
Hello fellow educators, my name is Aamir Fidai and I'm a math teacher. Currently I'm earning my PhD at the Texas A&M University, where I also teach integrated mathematics to future math and science teachers. In addition to teaching, I'm also engaged in research in the field of STEM education. I'm interested in exploring how exposure to STEM fields, careers, and people during the elementary, middle, and high school years of a student's life relates to their engagement in STEM academic fields after high school and their interest in STEM careers. I'm also actively researching how equity and lack of it plays a role in how different groups of students receive different levels of exposure to STEM education. I'm a big believer in defining moments. I feel that we all have defining moments in our lives, moments that give us a clearer view of our world, moments that give us answers that we seek, but more importantly, moments that give us questions. Because it's not the answers that change the world, it's the questions. My defining moment came when I built an electric bicycle and started riding it to school every day. We were living in Carrollton, Texas at that time, and the school where I taught was in West Dallas, 21 miles away from home. For me, my electric bicycle was simply a mode of transportation, something that helped me save time, gas, and more importantly, money. But something strange started happening as more and more students found out about my electric bicycle. They seemed intrigued to see an electric bicycle, as it was as if they had never seen an electric bicycle before. And guess what? They had not. They had never seen an electric bicycle before. That was my defining moment. The realization that my students had never seen an electric bicycle before. That brought about my big question. What else do my students from this impoverished inner city neighborhood do not know about? That students in more affluent neighborhoods would see as everyday knowledge. One of the consequences of this personally monumental defining moment was that I immediately started a STEM club at the school with a few of my students. I talk about the inception of this STEM club and how it extended my understanding of my students' need in a talk at TEDx conference in May 2016. The title of that talk reflected the defining moment I had just experienced. The title was, "They Don't Know What They Don't Know." I strongly encourage you to watch that TEDx talk once you're done watching this talk. My goal today is to share with you how I used the rebuilding of the electric bicycle as a PBL, or project-based learning activity, to introduce my students to the engineering design process, and the BSCS, which stands for Biological Science Curriculum Studies 5E model. Obviously, it is not enough that we experience a defining moment. Realizing the big question hidden behind that defining moment is just as important. And once we realize that question, we can't just let it be, especially as educators. When that question concerns our students, we must feel compelled to find the answers. So, once I realized that my students were facing a problem of exposure to science and technological knowledge, I had to try and find a solution. For me, the answer was in the form of a project-based learning activity. And what better activity to engage my students in than building an electric bicycle together? Because that was something that I was good at. The engineering design process that I engage my students in is simply an extension of the scientific process students learn in their science classes. Most of your students should be pretty familiar with the scientific method. They're exposed to the basics of the scientific method very early in the elementary school. I have a first grader who came home one day and started making observations and constructing hypotheses. I don't really know if he learned it in school or by watching the Nature Cat on PBS. But in any case, I think general education teachers do a very good job of exposing students to the scientific methods. So first comes the observation, which leads to questions. The questions encourage us to do research. Research leads to some kind of a conclusion or a generalization. This generalization is called the hypothesis. Now, to check the validity of the hypothesis, experiments are conducted. Data is gathered and analyzed, and the results are communicated. At this point, the hypothesis is either proven valid or invalid. The engineering design process works in a very similar way. The engineering design process begins with identification of a problem and the constraints attached to that problem. To solve the problem, research is done. It's undertaken by either an engineer or a team of engineers. The research leads to ideas for a product. The ideas are analyzed for feasibility. The product is built. It is tested and refined. And then the results of the testing and refinement are communicated. So let me share with you briefly how I implemented the electric bicycle project in the STEM club. You may want to use a similar project or this project or any of the hundreds of other projects available throughout the academic resources, online and offline. The first thing I presented my students with was a problem statement, which went something like this. Mr. Fidai takes a bus home from work. He does not like to wait at the bus stop. He lives 20 miles away from school. Mr. Fidai wants to build an electric bicycle to commute between home and work. Commercially available bicycles, electric bicycles, are either too expensive or too slow. Can you help Mr. Fidai build an electric bicycle that is fast and affordable? The goal here was to get the students to identify the problem in a real-life context. In addition to providing students with a problem statement, I also provided them with a list of constraints relating to the problem. I told the students that their ideas and possible solutions had to live within these facts. There's only a limited budget, $500 to $1,000. Speed is supposed to be limited to 20 miles per hour. Well, that's the law in Texas. The bike should have a range of at least 20 miles on a single charge. Remember, Mr. Fidai lives 21 miles away from home. There will be some pedaling involved. Mr. Fidai should be able to recharge the battery for the bicycle away from the bicycle. So I could take the battery out, take it to my classroom, and charge it there as I teach. And the bicycle should be suitable for commuting to and from work, which means that bicycle should have storage, necessary safeguards to keep the rider safe, the clothes safe from getting dirty or wet during bad weather. And trust me, I rode my electric bicycle in bad weather. During this phase of the design process, I asked the students to research possible solutions to the identified problem. I also encouraged them to treat every solution as a viable solution. During this phase of the design process, students researched possible problem solutions. They researched the material, the labor, and the expertise needed to implement those solutions. For example, the range requirement of the electric bicycle encouraged the students to look for batteries that have a range of 20 plus miles. Now, to the students' surprise, batteries are not rated in miles. They're rated in amp hours. So that's an example of how researching solution will drive the related conversations and add to the students' knowledge base. Here, an example of a sample lesson you can implement with your students when they make their realizations about the battery being measured in volts and amps. You can help them understand the connections between the amps and the volts and how all of that relates to the range of the bicycle. For example, you can begin by explaining that power is a product of volts and amps. Volts stand for voltage and amps are the measure of current. Similarly, power is denoted by W. So for any given battery, you can calculate the power output for that battery using the voltage and amp information. Next, share with them that motors are also rated in terms of voltage, amps, and power. For example, this typical 250-watt DC motor can run using 24 volts, 36 volts, or 48 volts batteries. Doing some math, we can see that running on 24 volts, this motor would require 10.42 amps to reach its full power potential of 250 watts. But the same power can be reached using only 6.94 amps if the voltage is raised to 36 volts, and even less current is used if the voltage is increased to 48 volts. Here, encourage your students to explore the inverse relationship between the current and voltage required to reach any given power level. Once your students have made the connection between volts, amps, and watts, it is time to check for understanding. You can begin by showing them a diagram where a 24-volt 10-amp battery is connected through a controller to a 250-watt motor. Encourage your students to determine if the battery would have enough power, enough voltage, and current to power the motor at full capacity for at least 1 hour. Make sure to ask them to justify their answers. Make sure to ask follow-up questions. Make sure to accept answers from as many students as possible before settling on one answer. Make sure to ask follow-up questions. It is important, that's why I'm repeating it. But most importantly, spread your questions and follow-up questions among all genders in your classroom. Meaning, ask your non-male students just as many follow-up questions as your male students. After discussion, your students should be able to tell you if this battery can power the motor at 250 watts for at least 1 hour or not. What do you think? Can this battery power this 250-watt motor for at least 1 hour at 250 watts? The answer here should be no, because the amp requirement is 10.42 amps, but the battery can only provide 10 amps constantly for 1 hour. Any more, and it will not provide the 10 amp for 1 hour. Do another exercise with your students. This time, let's change the setup a little bit. Instead of 24 volt 10 amps, let's do 36 volts 10 amp. Can this battery provide the motor with 250 watts for at least 1 hour? And here the answer should be yes. The battery should be able to provide enough current to the motor to run at full capacity for 1 hour. Once the students had researched ideas for the solution, I encouraged them to brainstorm possible solutions using the possible designs, using the findings from the research. I also encouraged them to keep the defined constraints in mind when brainstorming possible designs. For example, going back to the range requirement, hopefully they made a connection during the research between the range and the range that the battery can provide, its relation to the amp hour units, and the cost factor. This phase of the design is where you take what you have found during research and choose the appropriate components to apply to the solution. The ideation phase that follows is also when the STEM subjects make their way into the design process. For example, going back to the range of the bicycle not only depends on the amp hour of the battery, it also depends on the gear ratios employed by the motor gearbox and the bicycle itself. The diameter of the wheel impacts the speed and range as well. At this point, the students will need to use their algebraic and numeric skills to determine the optimum size of the tire, the RPM of the tire, the RPM of the motor, the gear ratios between the motor and the gearbox and the rear wheel, and the amp hour needed for each gear. So that all of this could be put together to find the motor, gearbox, battery, wheel, and other components that provide the maximum range, required speed, at the minimum cost. The ideation phase runs into the analysis phase, where students put their ideas on paper or computers and use their mathematics and possibly physics skills to test the feasibility of their proposed solutions. During this phase, students look at each component as it relates to the bigger system and vice versa. All ideas are analyzed using the requirements and the constraints, and the solutions that prove to be mathematically and physically sound are selected for initial build. This probably is the most exciting phase of the design process, the build. Students love this phase because they get to build the actual product. In this case, the electric bicycle. Students are excited and they do not even mind if a heavy motor accidentally drops on their foot. Don't worry, that never happened. So do you tell your students about the Murphy's Law before they start the build or after the initial failure? If you don't know what Murphy's Law is, here it is. Anything that can go wrong will go wrong. I prefer to wait until the initial failure, just so that the students can experience the failure and learn from it. The build will serve multiple purposes. First, the students get to see their idea in a physical form. And second, the idea is tested for the first time. The students get to experience what all great inventors throughout the history experienced: the thrill of success and the sorrow of failure. Either way, the students will be able to see all the work they did on paper in a physical form. This is important. This physical manifestation of their non-physical knowledge may work and it may not work the first time around, but for most of your students, the build will serve as a turning point in their understanding of what engineering is and how the engineering process works. Once the students have put together their first electric bicycle, it would be a good idea to explain to them that what they have made can be considered a prototype. A prototype, you might want to explain, is not the final product, but is something that needs to be tested and assessed for quality and imperfections. This is also the phase of the project where we actually test ride the electric bicycle. Now, when we made the bicycle with my students and it was time to ride the bicycle, I took the first turn because, well, obviously it was my bike. No, not for that reason. I wanted to make sure that the bike was safe for the students to drive, to ride. These electric bicycles can be very, very powerful, and things can go wrong in a hurry. So if you plan to work on this project with your students, make sure that you know how to ride a bicycle. During this phase, students should be encouraged to keep detailed documentations on the testing and refinement outcomes, since these notes will help finalize the design and will help the building of the final product. Now, once the first test ride goes well, and you have checked to see that the brakes work and the motor cutoff works and the bike is not falling apart, then it is fine for you to let your students ride the bike and experience the physical product that they have built with their non-physical knowledge. In this phase, the students also learn about the immediate shortcomings of the prototype, and through their further testing, they would find all the ways that the bicycle fails to meet the requirement and to stay within constraints. This is a great time to explain to the students that the engineering process doesn't stop with the first build or the first testing. It continues with refinements and retesting. And if after refinements and retesting the prototype still doesn't perform the task it needs to perform, then we might have to circle back to the beginning of the design process and re-identify the new problems and go through the process again. All the information you have provided your students so far can be found scattered in many books and websites. all the math, all the physics needed is present in textbooks, most of which your students probably already have come across already. However, to take all that scattered information and to put it in one place with a context is what makes the project-based learning approach more effective than others. As the students work on this project, they will work within the context of being an engineer. They will be working with a real-life problem, looking for a real-life solution within a set of constraints and specific requirements. This makes learning real for them. I feel that there's a growing divide between math and science education and the real life that our students live every day. And I strongly feel that hands-on activities that are situated in students' real-life context, something that the student can relate to, is a great way to bridge that gap. As educators, we must remember that students are children first, and even before that, they're humans, just like you and me. And they do get bored. So make math and science education fun for them by making it real. I hope you got to learn something from this talk. I hope you decide to build a project similar to this. And for more information about STEM project-based learning, read STEM project-based learning and integrated science, technology, engineering, and mathematics STEM approach by Caprero, and Morgan. Thanks again, and good learning.